Hello students, in this lecture we shall be talking about deposition, rate monitors, and process control. In 10 films deposition. Now, the first rate monitor that we shall discuss is the ionization gauge rate monitors. Now, this rate monitor works on the principle that it monitors the atom intensity in the vapor which has been produced for deposition by ionizing the vapor. And that ionization leads to an ion current which is measured. So this is how the ionization gauge works. The second method of rate monitoring is particle impingement rate monitor. Now, in particle impingement rate monitor, you have a thin aluminum cylinder suspended into the system, and the particles which are getting deposited onto this, they cause a rotation of this aluminum cylinder, and this is an aluminum cylinder. And so, due to the impingement of particles, there is a momentum given to the cylinder, and which causes torsion. From that we can measure, or we can have an idea of the rate of the deposition system. Now, the third method is electron beam heated molten pool. Now, when you are allowing an electron beam to vaporize the material, you have a plasma sheet over it, and what happens is that due to this, the positive ions are beamed away from the pool. Positive ions are beamed away from the pool, and basically yes, there is a magnetic field. Now, suppose this is the pool and an electron beam is coming, and there is a magnetic field which actually bends this electron beam towards this pool where the molten substance or the material gets melted, you have molten substance. So above this you have a plasma sheet as explained here. So what this plasma sheet will do, it will eject out the positive ions, and the same magnetic field which was allowing the electron to go into the pool will cause the positive ions to go out of the pool. Now after these ions, these positive ions, they again form an ion current, and it can be used as a feedback loop to monitor, to control the evaporation rate. Now, the fourth method that rate monitoring is very well known. It's called mass spectrometry. Now, what happens is here, there is also an atomic absorption spectroscopy, or it is also called electron emission mass spectroscopy. Now, after we have, this is how we control the evaporation. Now, after the evaporation is controlled, what we need is we need to monitor the deposited mass. So, monitoring of the mass is also important, because basically how much film has been filled, the thickness of the film can also be known by monitoring of the mass. Now, in these monitors, the first one is of course the microbalance, which causes changes in the mass due to condensed atom, and it is supported by a quartz fiber wire deflection. The second method is using a crystal oscillator, having piezoelectric properties. Now here the resonant frequency by an AC field is inversely proportional to the crystal thickness. So we'll call it Fr. The resonant frequency is inversely proportional to the crystal thickness. Let us call it as T. T stands for the crystal thickness, and Fr is your resonant frequency. Now, what happens is that when this crystal is exposed to a vapor, the change in the angle with reference to an angle, the change in frequency and so this change in frequency will be compared to a reference angle, that actually which we can actually monitor the crystal thickness. Now, if we look into the deposition materials that we normally use, so we are mainly concerned with the metals, or elemental semiconductor, or we are concerned with the alloys. That means if you have, in case of alloys, however, if we have two alloys, A and B, and we somehow allow the vapor deposition from both these states, so this is the substrate, so this is where the alloy is formed, where both from A and B vapors come and mix. So you get an alloy AB. Now this process is complex, or the monitoring of this film of alloy is complex, because the evaporation from each source needs to be monitored separately. Now, in electron beam deposition, we have the feed usually is given. There are different ways by which we can give the feed to the system. By feed means the precursor material or the source material from where the films are to be made. Now, these feeds can be of different size and shapes, and different mechanism by which these feeds are given. Now, in case of an electron beam evaporation, we have a feed which is called single rod feed electron beam source. So here we can have either a rod feed or a wire feed. So say this is the rod, so when we are allowing electron beam to fall on it, so the molten pool is created at the top. And if again here, if A and B are two different rods that we are using, so each of them will have different vapor pressures. Like, so suppose the difference in vapor pressure is that the vapor pressure of B is 10 times the vapor pressure of A. So in the feed, the vapors are, or the composition, you can call it as A1, B1 or A, but in the molten case it will be A1 and B10, the molten pool after the moles. So this is the change that one has when we are using the different vapors from different sources. Now, under steady state conditions, the composition of the vapor is the same as that of the solid fluid. But this is quite not what we get in a practical case. Now, what happens when we deposit in, this was all about alloys, what happens when we deposit in an intermetallic compound? For example, if we are using gallium arsenide or lead telluride or indium antimonide as the constituent elements, and these materials have the property of low melting point and high vapor pressure. Now, if our objective is to develop a compound semiconductor, so in that case we need to have a careful controlled stoichiometry. So this have a controlled stoichiometry. Basically, by stoichiometry we means a cation to anion ratio, and the evaporation of intermetallic compounds is mainly done either through flash evaporation or it can be done through sputtering. These two methods are mainly used to deposit an intermetallic compound. Now, in a flash evaporation, the powder or chips of the two components are sprinkled onto a superheated sheet. So, powder or chips of the two components are sprinkled onto a superheated sheet. Where the basic thing is sprinkling, it should be sprinkled, and there is a superheated sheet, and it is done so that the complete evaporation of the components take place. Now, if you look into the different types of feeders, we have something called a belt feeder. From the enamel belt, you will understand that there is a metal belt, and this is the boat, and this is the feeder. So you put the material inside it, and you remove the belts. At a certain point of time, the material goes inside the boat. This is the boat which is in contact with the heat source, and this boat is mainly made up of molybdenum. Uh, so next type of breeder is a warm drive breeder. So it looks, so we have a gear. It rotates, and this is a hopper where you put the source, and there is a spring attached to it, and there is a tungsten strip, and this is how the material falls onto this tungsten strip, and it is called a chute, C-H-U-T, chute. And this is, I've told you, this is the gear. So this is how the gear rotates, and the feeder is given from into this hopper. It rotates and ultimately transfers the material into this tungsten strip. This is called the warm drive feeder. Another type of feeder is called the disc feeder, where this is the hopper, and you get a disc, and rotates, and it converts, and it allows the material to fall onto this aluminum strip. And we have another component, it's called the drive shaft. So apart from that, there are different types of feeders, and which are used to feed the precursor material to the place where it ultimately given heat. Now these are all the metals. What about if you would like to deposit deposition of refractory compounds? The compound with very high melting point, and it mainly consists of ceramics, like you have oxides, nitrides, borides, sulfides, etc. Now, in some of the cases when we are depositing refractive compounds, they form extensive defect structure, and these defects they actually stay and exist over a wide stoichiometric range. And for example, if we deposit, say, titanium carbide, so in that case the carbon and titanium ratio can vary from 0.5 to 1.0. And if it is 1.0, so higher is the number, higher is the shift from this equal amount, equal concentration to 1-sided concentration, so the vacant lattice site concentration increases. It's quite obvious because when you are depositing say two materials A and B, so let's say we have AB, AB, BA, BA, AB, AB, and BA, BA. So at this point of time, there are equal number of A's and B's. So the A and B ratio is 0.5. Now, if it shoots towards 1, or say it is going to say 0.7, so it means that now the A concentration has increased while compared to the B concentration. So it means that some of the B's have been removed. So we get some vacant lattice sites. So this is how if the ratio increases, the chances of vacant lattice site also increase.